Hi, everybody. I'm Radinsky. I'm the CEO of Diagnostic Robotics. For the last few years, we've been seeing more and more growth in the number of people going to the emergency departments. It's been growing so fast, even faster than the growth of the entire population. In other words, we have a growing old population. So the 3.6 hours that we're waiting right now, on average in the emergency department, will drastically grow over time. In the next 10 years, we're going to have 3.8 billion people without access to primary care. So the 3.6 hours estimate will quickly become 8 hours of waiting time, like we already see today in China. So in the last few years, we started building systems that try to take the process inside the emergency departments and in primary care physicians and automate part of this, especially the triaging part and the proactive care part. We have access to more than 19 million articles, 60 billion historical visits, and we receive information about the medical records, lab results, EKG, time series data, and others. And we build a system to read all of this information and extract patterns to help triage and navigate those patients. In clinical trials, we have those AI stations positioned. While patients are waiting to be triaged by a nurse or a physician, the system is asking them a set of clinical questions and predicts how to navigate them. In clinical trials, we've been trying inside hospitals. In production system, we've been doing these processes in home and even in primary care. In primary care settings, the way it works, while patients before they schedule an appointment with a primary care physician, the system is asking them a set of clinical questions. For example, does it hurt when urinating? Do you have a lower abdominal pain? Predicts behind the scenes based on all of this historical information what is the best next step for the patient based on historical information. For example, if the diagnosis is UTI and it's 30% by diagnostic robotics scoring system, the physicians have wrote a rule saying that everything about 30% should do a urine test before meeting with the physician. After the result is coming back to the medical record, the system updates the score to 90%. A physician outreach to the member with antibiotics. The way we built this, we had access to 76 million medical records, medical summaries in free text for approximately 500,000 patients. And we started building a system that can actually get all of this information, extract answers to clinical questions written by the clinical team. Once we had answers for each patient, we started building a machine learning pipeline that looks for correlations between those answers and the decisions physicians have made in the past. So how does it work from a natural language processing system? The system needs to identify all of the historical conditions of the patients. For example, this is a condition the patient suffers historically and not now. Then the system needs to identify the type of medication and whether they should be worried about them right now or they've been taking them in the past. The system also identifies current conditions, but also gets to the granularity of, for a headache, whether it's interior or exterior, how heavy it is, how long it's been taking. Behind the scene, we have ontology around all of those symptoms, and the system is matching based on natural language processing to one of the phases in these ontologies. And of course, the system also has to identify negations. Therefore, a lot of systems that only rely on keywords are not enough. The way we build this, we had medical students read all those medical summaries and, for example, mention negation. We then built a lot of deep learning models trying to mimic those physicians and predict this. Another problem that we saw many times in those free texts is that not all the entities are mentioned in the text implicitly. For example, in this case, the patient was admitted with a hypertension along with accompanying conditions. The underlying condition, which is not specifically written here, is tachycardia. So we actually had to deal with additional issues of identifying entities not actually written in the text. The way we build this, we build a form of variational autoencoders, taking a text and trying to recreate the entities which are not mentioned in the text itself. All of the labels are coming from the medical students. The system is learning on them and then applying on the other 70 million medical records and summaries. We then started building a system that takes all of this information and builds a machine learning model, mapping those entities to a label the physician has done in the past. For example, for a headache, should the patient be sent to an emergency department or not? Should we do an MRI or not? Here I'm showing you the actual clinical results. For 76 million visits, we were focusing on only headaches. Approximately 500,000 headache complaint is a chief complaint. We had a training set, validation set, and a testing set. We started building several machine learning models empirically and reached an AUC of 83. But one of the problems that we started seeing when we started applying this model in prospective studies is that the AUC started dropping to almost 50 or 60. And I'll tell you the main reason. Out of all of the patients complaining about the constant pain in the chest, how many times do you think the doctor actually documented a constant pain in the chest? The answer is 20% of the times. 60% of the times the physician actually documented that the pain comes and goes, and 20% that the pain disappeared. 21% of the patients with a chest pain said that it radiates to their left side when asked by the digital triage system, but the physician only agreed with less than 5%. So the main problem that we have here behind the scene is, although the algorithms are pretty accurate, an AUC of more than 80, for some diseases we get to even more than 90, there's a distribution change between how patients are answering and how physicians are documenting. So the machine learning models were running on completely different distributions. So a lot of the work that we've been doing for the last years after running on 30 million patients on a monthly basis is starting to align those distributions, making sure that based on the answer of the patient, the physician is actually documenting something very similar. I'll give you an example. Instead of asking the patient, is this the worst headache of your life? We altered the question and asked, does it feel like lightning hitting your head? We identified that once we asked this question, the distribution between what patient reported and what the doctor reported as well was very similar. So it's all about getting the questions in a correct way so distributions will match. And here's the results of the clinical trials after all of the alternations. We had access to almost 1 million emergency department visits. Out of them, 30,000 emergency department visits with a headache as a chief complaint. We had a little bit more females than males, mostly young patients, less elderly patients. This has been run in a large hospital in Israel called Rambam. And the resulting of the system, we see that 80% of the time, diagnostic robotics model got correct the right diagnostics. The problem is, it's not enough. But if we look at the very first 2 diagnoses the system gave, it had already 93% accuracy, and if we look at the top 3, it's already 98% accuracy. What we actually learned here is if you tailor the system to predict diagnosis based on only questions from the patients without any physical test, it's not enough. So instead of trying to get to the right diagnosis, we've been focusing a lot on getting the right differential diagnosis. Additionally, we started focusing on not only getting differential diagnosis, but actually preparing the patient to the meeting with the physician, getting them all the tests done so the meeting itself will be super efficient. We actually started predicting different tests because asynchronously, while the patient is waiting, we can start navigating them to different tests. So we started getting AUCs around 75, 80, but getting a much higher efficiency inside the hospitals. So one of the main things we were thinking is, can we learn a machine learning models on medical text coming from hospitals, primary care physicians in the United States and Israel, and think whether it can be applied somewhere else in the world? So here I'm showing you a completely different transfer into a different population from 100,000 Singaporean soldiers. And we see that the model that we train, for example, for predicting sinusitis, reach an AUC of 89. When we apply exactly the same model on a completely different population in Singapore, we get a very similar result. So what we understand is that for diagnoses which are not chronic, but mostly acute, we see that the distribution is very similar. One of the main problems of relying on only medical records is that it only identifies correlations. And therefore, the questions that we're asking do not actually have a cause and effect, impact. And therefore, we were thinking for a long period of time, how can we make those questions much more unique? Giving you an example that we identified from the EMR, psychiatric patients are more likely to suffer from Parkinson's disease. Unfortunately, this is only a correlation because Parkinson is a side effect of some psychiatric drugs. So the next action we start doing is thinking about how can we create a causality graph driving our triaging questions, instead of asking the patient so many questions that some of them are correlation rather than causation. The way we built this, we took 19 million articles, mostly taken from PubMed, constructed a graph based on the text of those medical journals. What we then started doing is walking on this graph, identifying right causalities, and then identifying if the same causation we identify in the PubMed articles is indeed also present as a correlation in the medical records to reduce the number of false positives that we have. So here's an illustration of the process. We would get sentences like malabsorption was found due to celiac disease and break it down to an entity, predicate, and object. We started from templates and then studied deep learning models to actually start learning only between the subject and the object in a more coherent way to increase our data. We then started building different type of graph walks to identify which type of entities cause each other. And we started getting to a 50% agreement with cause and effect with senior physicians. One of the main issues that we had was around how can we identify whether it's correlation, causation, or just a problem in the data and the text. So once we started merging this with information coming from the EMR, it significantly improved the results. But one of the main problems of relying on only medical records, but also on medical text, is that it has a lot of bias. What we learned is for certain types of subpopulations, like females, for example, till 91, not a lot of females were included in clinical trials. What eventually got to a point where if you don't have enough females, the entire clinical results do not always apply for them. So let's take one example. The subpopulation of women having hepatitis C is around 50-50, 50% males, 50% females. But in clinical trials on average, only 35% of participants were women. Let's take the other way. In fibromyalgia, although only almost 60% of the patients suffering from fibromyalgia are females, 92% of the participants were females. So what we actually started also seeing is that it also changes drastically based on different diseases. And if we start applying machine learning models on this, and specifically on medical journals and the text there, we're amplifying this bias, especially as afterwards we're applying this for different types of medical text. So what we started doing is trying to build embeddings of the different entities based on how many clinical trials you have there based on their gender. Very simply put, we also have information on how many female participants and males, and we would actually give higher weights to the word if we have more women in that trial, if we're building a women-oriented model. The results itself were extremely significant. We're building our deep learning models, and we saw that when we're relying on gender-sensitive embeddings, in other words, giving higher weights to articles where they had more women as opposed to other ones which were not, we saw a huge increase in the area under the curve for many tasks. For example, ICU readmission. We saw this specifically a big raise for females, but also a slight increase for male. And the reason is studies that have a good number of males and females based on their real distribution in the community probably have much stronger results and are much more predictive. But I started this talk with discussing that for the next 10 years, we're going to have 3.8 billion people without access to primary care. So, what can we do to actually make an impact? So, it should not only be deployed inside emergency departments, it should be deployed through all the primary care facilities. And we've been lucky enough to start deploying this for almost 28 million patients' usages on a monthly basis, getting results for all those members and making sure that we can navigate them to start providing more primary care to more patients. Thank you very much for your time.